In this video, I will describe the process it took me to burn an actual AI onto custom FPGA hardware. As always, I encourage you to watch until the end and fight the brain rot, as this project is full of valuable lessons. FPGA. The first time I heard about such thing, my mind couldn't really comprehend. Firstly, because I was, and I'm still am, an aerospace engineering major, and also because it blew my mind that one could create any circuit he wanted using actual programmable logic. I mean, you could do anything with that. So you literally start from the ground up and work your way up from the lowest level possible to a fully working solution, in our case, an AI model. And before talking about how I ended up burning AI on this FPGA thing as my first freelance mission, we need to lay down a bit of context first. If you watched my previous video on Zinc, you know a professor of mine once came with a project idea based on FPGA. This project was a computer architecture contest organized by one of the top French defense and tech company. The goal was to accelerate a convolution neural network on a RISC-V processor. And after a lot of efforts, I actually lost. I lost from very far, by the way. They absolutely crunched me, but I still made very valuable and very original improvements that were actually working. After that, I felt like I could do anything if I put my mind to it, and I was absolutely right. You could do it too, actually, and that's why I started this YouTube channel. I also thought this knowledge was very bankable indeed, because yeah, I mean, business is business, let's not forget the basics. So I decided to sign up for freelancing. I thought that no one would give me an opportunity on this field, so might as well make it happen myself. After doing some grinding on small missions and projects, I stumbled upon an intriguing post on someone who wanted to run an AI onto an FPGA. This sounded like a hard project, but I needed a challenge, and I had some past experience that would play as a huge asset to get the job done. It was no time to get the job done, but how? There was no RISC-V this time, and even though I knew my way around AI and FPGAs, I felt like there was so much things that could go wrong in this project, and I was right indeed. So where do I even start? What firmware do I even write? And wait, how do I even get an AI onto FPGA in the first place? And how do I handle training? And how do I handle floating points? Oh my god. There was so much questions and concern, but that turned out to be the perfect thing for this mission, as this is about teaching. Wait, did I not tell you? This entire mission purpose is to create an entire 10-hour course on the whole process. Whoa, that will not be easy at all. But starting from where I was as a lost engineer trying to solve a problem was the perfect way to put myself in the shoes of the people I would teach the course to. Anyway, now was the actual time to start. I had deadlines to meet and my reputation as a freelancer and engineer was on the line. Let us now see how did I manage to make an AI literally from scratch on an FPGA as my first freelance mission. When it comes to such projects, it's hard to know where to start. Fortunately, if you know your way around AI, you know that simple classifiers can be pretty damn simple. For those who don't know, a simple neural network consists of nodes organized in layers that just does a sum of multiplications, also known as the MAC operation. This operation is very simply implemented in hardware, and if someone can get his hand on the AI weights, aka parameters, the things that you find through training, then this person just has to create simple hardware layers and imports the weight inside and simply execute the model. But if it was that simple, everybody would do it, and even if this workflow sounds great, it is far from scalable to large and complex architecture, as any modification anywhere will translate in a huge code-based change all around the project. To solve this project, I used the Fin tool developed by Xilinx. Fin allows me to translate a neural network into these hardware layers with a simple Python API. It also includes very useful and easy to use handles for efficient workflow. I won't get into the details of this tool and the other various tools I used because it is way out of the scope of this video. But you get the idea, and I plan on doing a tutorial on this, so stay tuned. With this first concern out of the way, I had to actually come up with an AI model to run. This usually wouldn't be a problem, because I will use a simple, fully connected classifier, which is one of the simplest AI architecture everyone uses for their proof of concept out there. But one big problem still remains. Remember the MAC operation? When working with very low-level project and low computing power environments, you want to think about the cost of your computation. Running MAC to compute tensor operation is pretty expensive by itself, but you know what is even more expensive? Floating points operation. That's what. In computers, numbers are represented using a certain number of bits and encoded using a certain data type. Floating points allow users to represent huge amount of numbers, including fractions, but this operation requires specific and expensive computation units. People take floating points for granted, but they are far from trivial, and in FPGA, we have limited resources to work with on the silicon, meaning we won't use floating points. The problem is that AI is always trained using floating points operations. Why? You tell me, but there is a way to get around this. The solution is called quantization. Quantization allows us to represent data using fewer bits and also in another well-known data type, integers, which is the native way of representing numbers in Boolean algebra, making it very, very cheap to implement. The quantization process induces some error. Thankfully, this error is neglectable for most of the use case, and that will do it for us. With that in mind, time to train our quantized neural network. For this purpose, I will use Brevitas, also made by Xilinx, that works just fine with Fin. Now that we have an optimized model and a hardware version of it, it's time to actually put it onto an FPGA. To do so, Fin gives you some Python API calls, but it works only on supported boards. And because I like to solve problems, and mainly also because I didn't have a supported board, I decided it was better to do it manually. Little did I know, that was the hard way, as it requires to implement all of the subsystem yourself in a coherent and robust architecture. It also implied writing the firmware myself to leverage the design. So, I started making a project and started stumbling upon multiple problems. The worst one I had to debug was the non-compatibility between the data interfaces between the model Fin gave and the coprocessor that was in charge to move the data in and out from the system memory. Long story short, I ended up doing my own block to interface between the two, and it pretty much ended up working just fine. Regarding the firmware side, it's pretty simple and straightforward. It moves data in and out of the model. This data was generated using a very simple Python script. The whole system uses UART to communicate with a human user, and for the demo I simply classified 100 sample, which allowed me to compute the model accuracy. Well, it depends on what performant means for you, and I'd say it all depends on your requirements. Just to give you an idea, I was able with my non-optimized model to get about 650,000 FPS. Given that each frame is 784 bytes, that means that the model throughput was about 510 megabytes per second. On a small Zinc FPGA board, I think this is pretty good. And this was only using 20% of the resources. According to the Fin paper, similar performance used about 5 to 20 watt of power. So yes, it's far from new 4090 in terms of performance, but in terms of power efficiency and embedded throughput, we are pretty damn performant. This begs the question, what is this even good for and what are the use cases? When it comes to use cases for this, you have to think about embedded device and privacy. First of all, running the AI on FPGA close to the data source, which is a technique called edge computing, will give you control over the data for the privacy aspect, but also allow for a very low delay real-time solution with a low power consumption. This makes it a great solution for classification on production lines and also a great option for privacy-oriented IoT in general. Yes and no. FPGAs are a Swiss army knife when it comes to digital computing and data processing or sampling. But while Fin, the tool I used, does take into account most scenarios, some shady architectures and AI techniques may not be yet implemented. You can implement them yourself if you know your way around it, or even contribute to the Fin codebase if you want to.